Hello viewers, I am Kausalya. Today we are going to see the derivation of RC Transients charging part. So here a DC voltage E is applied to a series RC combination. So here we are having resistor and capacitor connected in series, and to that combination we are applying a DC volt, okay, which is denoted as E. So here, since we are dealing with capacitor, right, let Q naught be the initial charge on the capacitor. Therefore, V naught be the initial voltage on the capacitor. And as we all know, the capacitor is given by, the formula is voltage across the capacitor is given by Q naught by C, and C is nothing but the capacitance value, which is usually expressed in terms of farad, right? So this is the circuit diagram, right? So here you see all these three elements are connected in series, and the source voltage and RC are separated by a switch, right? So after closing the switch, when you apply Kirchhoff's voltage law, right, when you apply KVL, so here the expression is, that is, sum of voltage drop is equal to sum of voltage rise in a closed circuit. So here the voltage rise is nothing but our source voltage E, and voltage drop is nothing but it is the voltage across your resistor and your capacitor, right? So here it is given by, you see, I into R, that is voltage across the resistor is given by I into R. Let I be the current that flows through the circuit, right? And voltage across the capacitor is given by 1 by C integral of, right, minus infinity to t, I into dt. So here this is the expression for voltage across the capacitor, and here the summation of these two is equal to the source voltage E, right? Now here the thing is, that is t denotes the time duration till the switch is closed, right? And here let the lower limit be minus infinity. Now we are again going to split this integral part into two forms, right? Here the one is, you see, the limit is minus infinity to 0, and the next thing is 0 to t, right? So here this minus infinity to 0, that is, this entire expression denotes the initial voltage, that is, before switching on, right, before switching on there may be some charges present, okay, some charges present on the capacitor, and due to those charges we may have some voltage across it. So here that is denoted by this limit, okay, before switching. That is the main reason why here we are having 0 as the maximum limit, right? So this is the initial voltage. So initial voltage is denoted by, that is given by this V naught, right? So just replace this entire expression by V naught here. Therefore IR plus V naught plus 1 by C integral of 0 to t I into dt is equal to E, right? So as we already said, we are considering the initial voltage on the capacitor be 0. That is, the value of V naught is 0, or this expression is 0, right? So when V naught is 0, our expression reduces like this, right? 1 by C integral of 0 to t into I into dt is equal to E here. Now we are going to take Laplace transformation. So when you take Laplace transformation, you see our expression gets modified as I of s into R plus 1 by C. Here I becomes I of s, and because of this integration we are having divided by s, which is equal to E by s, right? Now I am taking I of s term commonly outside. So the remaining expressions are R plus 1 by Cs, which is equal to E by S. Now I of S is written as E by S into R plus 1 by Cs, right? Now I am going to multiply this S with these elements. So when you multiply, you see our expression gets modified like this, right? SR plus 1 by C. Again from this expression I am taking R commonly outside. So when you take R outside, you see our expression is S plus 1 by RC, right? Therefore, I of S is given by E by R into S plus 1 by RC, right? So we are going to take inverse Laplace transformation. So I of t, I of s becomes I of t. Here E by R, this is a constant thing, right? E is voltage and R is the resistance value. So E by R into, when you take inverse Laplace transform, S plus 1 by RC becomes e to the power minus t by RC. Right. So as we all know, E by R is nothing but it is our current, and here RC is the time constant, and this is denoted as lambda. Right, now we are going to rewrite the above expression. So when you rewrite, you see I of t is equal to I into e to the power minus t by lambda. Right. So here in this expression, we are going to substitute different values of t, and thereby we are going to calculate the values of I. Right. So here when the value of t is 0, right, e to the power 0. So that the e to the power 0 becomes 1. Therefore, I of t is equal to I. So I is equal to capital I. When you substitute the value as infinity, then this e to the power infinity becomes 0. So 0 into I becomes 0. Therefore, the current becomes 0 here. So now we are going to draw this as a graph. Right. So here you see, this is your graph part. Right. When the value of t is 0, what is the value? The value is I. So here you see, when the value of the x-axis lies t, so here it is 0. When the value of t is 0, the maximum value of the current is capital I, that is E by R. Right. But when the value of t is infinity, right, what happens? The value of current becomes 0. So here in this case, it is clearly shown that whenever the time starts increasing, right, you see the value of current gradually decreases, and after some time, that is after longer time, right, when t becomes infinity, then the value of current will become 0. Right. Now we are going to calculate the voltage across the resistors and capacitors. So here you see the voltage across the resistor, it is given by the basic formula I into R. So just now we have derived an expression for I. So this is given as I into e to the power minus t by lambda. Right. So here this I into R, it is nothing but our E. So this is given by E into e to the power minus t by lambda. Right. Now the next thing is we are going to find the voltage across capacitor. So here you see ER plus EC is equal to E. That is voltage across resistor plus voltage across capacitor is equal to your supply voltage, again by KVL. Now when you substitute the value, you see EC is nothing but E minus ER, and the value of ER is given by this expression. Right. So just substitute the values here, and once you take the value of E as commonly outside, so our expression is EC is equal to E into 1 minus e to the power minus t by lambda. Right. Again, we are going to draw the graph for these expressions. Right. When you draw the expressions, you see here the voltage across ER is gradually decreasing, whereas the voltage across the capacitor is gradually increasing. Right. Now we are going to find the value of time constant. So here the expression for current is given by I is equal to I into e to the power minus t by lambda. Right. When you replace lambda as t, what happens? I is equal to I into e to the power minus 1, and once you solve, you see the final value of I is given as 0.368 times of I. That is, when you express this in terms of percentage, it is nothing but 36.8% of the initial current. So definition wise, the time constant is written as time constant for the RC circuit is the time during which the current falls to 36.8% of the initial current. Right. Now the next thing is, here comes the end of this derivation. Right. Now we are going to see this decaying transients, that is discharging derivation. So here consider this circuit. Right. So this is your RC decaying transient, that is discharging. So here you see again we are having the same circuit diagram, but the extra part is here we are having a position 2. Right. So this is your position 1 and this is your position 2, and let I is the current that flows through the circuit here. Right. So you see when switch is in position 1 for sufficient time to establish the steady state condition, that is we are keeping the switch in position 1, okay, so that a steady state current flows through this circuit, right? So here, now we are moving this switch from position 1 to position 2, right? So when the switch is moved from position 1 to position 2, what happens? That is a sufficient voltage across this capacitor, which is denoted as E here, right? Because when the switch is in position 1, right, the capacitor is charged to its maximum level, right? That is almost the capacitor is charged to this source voltage, right? So here whenever you write expression, you see when you apply KVL, again voltage across resistor, right, and voltage across the capacitor is taken into account. So here now you see the voltage across the resistor is I into R, right, and voltage across capacitor is 1 by C integral of 0 to t I into dt. Plus, you see there is a voltage which is stored across the capacitor when the switch is in position 1, and that voltage is not discharged. Okay, it is still present because we are instantly moving the switch from 1 to 2. Therefore, that is taken into account, which is denoted as E here. Right. Now we are going to apply Laplace transformation. So again you see here, this is our expression here. And now again we are going to frame an expression for current. So I am combining I of s terms together and I am moving this part to the right hand side. Therefore that becomes minus E by S. So when you take inverse Laplace transform, you see I of s is given by E by S, S plus 1 by SC. So whenever you are supposed to take this inverse Laplace transform, our expression should contain S plus some term. Okay. So here we are having R. So I am taking this R outside. So when you take R outside, this is how our expression will be. Now the next thing is I am going to multiply this term with S because I always need an S plus term. So when I move this S inside, you see here our expression becomes S plus 1 by CR, right? So here in this case, when you take inverse Laplace, you see our expression is e to the power minus t by CR, right? And here, as we already said, RC is our time constant, right? So therefore here in the place of RC, we are writing a lambda. So this is our final expression, that is, this is your I of t. Right. So I of t is given by minus I into e to the power minus t by lambda. So this expression for current is known as discharging current. So whenever you draw a graph, right? So whenever you draw a graph between your current and time t, so here this is how our graph is. Right. So this current is known as discharging current. Right. Here comes the end of this video. If you have any doubt, let me know in the comment section. Thank you.